On November 7, 1940, thousands of drivers considered a beautiful new bridge in Washington state completely safe. 4 months later, it was famous for a different reason. It tore itself apart in a windstorm, and someone caught it all on film. That's the strange thing about bridges. We build them to outlast us. Steel, concrete, decades of engineering knowledge, and yet, every few years, one falls. Not from an earthquake and not from a bomb, just from the road, the traffic, the wind, blowing exactly the way it always does. So what actually makes a bridge fail? Not in a slow, visible way, with cracks spreading for years while crews scramble to fix it, but suddenly, in seconds, with seemingly no warning at all. The unsettling answer is that most catastrophic bridge collapses aren't sudden at all. They just look that way from the outside. Underneath, something has usually been going wrong for years, sometimes decades, hidden inside steel and concrete where no one thought to look. To understand why bridges fail, we have to follow the small, invisible failures that engineers spend entire careers trying to catch before they turn fatal. This is the story of why bridges collapse and what it took for the world to finally understand it. A bridge does one job. It carries weight and passes that force safely into the ground. Every cable, beam, and joint is part of one chain. But like any chain, a bridge is only as strong as its weakest link, and in some of the worst bridge failures in modern history, that weak link was smaller than a coffee mug. Take that bridge from 1940, the Tacoma Narrows Bridge. Nicknamed Galloping Gertie by workers who felt it sway even during construction. Engineers had built it as one of the longest suspension bridges in the world at the time. What they hadn't accounted for was how the wind would move around its narrow, solid girders. For years, the popular explanation was that the bridge collapsed from resonance, wind hitting the bridge at exactly its natural frequency, the same way pushing a swing at just the right moment sends it higher and higher. It's a satisfying story. It's also not quite accurate. The real cause was something more unusual: aeroelastic flutter. As wind moved past the bridge deck, it created swirling vortices that caused the structure to twist as well as bounce. That twisting fed energy back into the bridge, and the motion grew larger and larger until the deck was rotating wildly, some sections tilting nearly 45 degrees. Eventually, the cables gave out, and hundreds of feet of roadway dropped into Puget Sound. Miraculously, no people died. Only a dog left behind in an abandoned car was killed. But the footage of the bridge writhing like a ribbon changed engineering forever. Watch it today, and it barely looks real. A two-lane highway rippling like water, cars sliding across a deck that seems to be breathing. It's still shown in classrooms today, not to prove simple resonance, but to show how little the field once understood about aerodynamics and long-span structures. That single failure rewrote the textbooks. Wind tunnel testing became standard practice for every major suspension bridge built afterward. Engineers started studying not just how much weight a bridge could hold, but how air itself would move around it. In a strange way, Galloping Gertie's collapse made every bridge built since safer, because it forced an entire profession to admit how much it still didn't know. Wind wasn't the only invisible enemy. Decades later, engineers would learn that some bridges don't fail because of a dramatic storm. They fail quietly, from the inside, over years. Metal fatigue is one of the most dangerous processes in engineering because it's nearly invisible until it isn't. Every time a bridge flexes under traffic, thousands of times a day, tiny stresses build up inside its steel. Over years, microscopic cracks can form at points of highest stress. Welds, bolt holes, sharp corners. A single crack might be barely visible to the naked eye, but it grows, cycle after cycle, the same way a paperclip bent back and forth eventually snaps. That's essentially what happened on December 15, 1967, at the Silver Bridge, connecting Point Pleasant, West Virginia, to Ohio. The bridge relied on a design most modern bridges avoid: I-bar chains, instead of the redundant steel cables seen in later suspension bridges. In an I-bar design, thick metal links connect together like a chain, strong, but with a critical weakness. If one link fails, there's no backup path for the load to travel. The whole chain goes with it. Investigators later determined that a single I-bar had developed a small crack from corrosion, likely invisible during past inspections, and it finally gave way under the stress of rush-hour traffic. The bridge collapsed into the Ohio River in seconds, killing 46 people. The disaster was significant enough that it directly led to the National Bridge Inspection Standards in the United States, the very inspection program that checks American bridges to this day. But even inspections and modern engineering can't catch everything. Sometimes the fatal flaw isn't corrosion or weather. Sometimes it was there from the very beginning, buried in the original design. On August 1st, 2007, during rush hour, the I-35W bridge over the Mississippi River in Minneapolis collapsed without warning, dropping cars, trucks, and a school bus full of children into the river below. 13 people died. Investigators from the National Transportation Safety Board eventually traced the failure to steel plates called gusset plates, the connectors that link a bridge's steel beams together at each joint. Some of these plates on the I-35W bridge had been designed only half as thick as they needed to be, a flaw dating back to the bridge's construction in the 1960s. For decades, the undersized plates carried the load without any visible problem, but on the day of the collapse, the bridge was undergoing repaving work. Construction equipment and stockpiled material, tens of thousands of pounds of concrete and machinery, sat directly on the deck, adding weight the aging bridge had never been designed to carry in that combination. The already marginal gusset plates finally reached their limit, and the center span gave way in seconds. Here's what connects nearly every catastrophic bridge failure in modern history. It's rarely one single cause. It's a chain of small, individually survivable problems that line up at exactly the wrong moment. A design margin that was thinner than it should have been, a material that slowly weakened over decades, an inspection that missed a hairline crack hidden inside a joint, extra weight added for construction, or heavier trucks than the bridge was ever designed to carry. Any one of these alone might not bring a bridge down, but when they stack together, the structure runs out of options all at once. And unlike a slow leak or a widening pothole, there's no gradual warning. The steel simply reaches its limit, and gravity does the rest. This is also why redundancy has become one of the most important words in modern bridge engineering. After the Silver Bridge tragedy, engineers moved away from designs where a single point of failure could bring down an entire structure. Modern bridges are built with multiple cables and multiple support paths, so that if one component starts to fail, the load can redistribute elsewhere, buying time for warning signs to appear before disaster strikes. Even so, the risk hasn't disappeared. In August 2018, the Morandi Bridge in Genoa, Italy, collapsed during a rainstorm, killing 43 people. Investigations pointed to corrosion inside the bridge's pre-stressed concrete cables that were sealed inside concrete casings specifically to protect them from the elements, but which trapped moisture instead, slowly eating away at the steel from within for decades before anyone could see it happening from the outside. That same year, a much newer structure failed in a very different way. In March 2018, a pedestrian bridge under construction at Florida International University in Miami collapsed onto traffic below, killing 6 people. Unlike Tacoma Narrows or the Silver Bridge, this wasn't a decades-old structure worn down by time. It hadn't even opened yet. Investigators found that cracking had already appeared in one of the bridge's structural members days before the collapse, and engineers on the project were aware of it. A design flaw combined with decisions made while the cracking was actively being investigated led to a sudden failure while workers were still adjusting tension in the structure. It was a sobering reminder that a bridge doesn't have to be old to be dangerous. Sometimes the countdown to failure starts before a single car ever crosses it. These disasters are also why bridge engineering looks so different today than it did even 20 years ago. After Minneapolis, states across the country began using more advanced inspection methods, ultrasonic testing that can detect hairline cracks inside steel without cutting it open, sensors bonded directly onto bridges that continuously monitor strain and vibration, and drones that can photograph high, hard-to-reach areas that inspectors once had to dangle from ropes to see. Some bridges now essentially report on their own health in real time, flagging unusual stress patterns long before a human inspector would ever notice them. None of this makes bridges indestructible. It just means the invisible failures have fewer places left to hide. That's the unsettling truth about bridge engineering. The same materials that make bridges possible, steel, concrete, tension, and compression working together, are also quietly aging every single day, long after the ribbon-cutting ceremony is forgotten. Most bridges never fail. Engineers, inspectors, and safety codes built from the lessons of Tacoma Narrows, the Silver Bridge, and Minneapolis have made modern bridges far safer than they were even 50 years ago. But every bridge is, in the end, a kind of bet. A bet that the design, the materials, and the maintenance will keep pace with time, traffic, and weather for as long as people need to cross it. Most of the time, we win that bet without ever noticing it was being made at all. Next time you drive across a bridge, take a second to notice it. The steady thrum of tires over expansion joints, the beams overhead, the water or highway passing beneath you. It feels permanent. It feels like it will always be there. But somewhere in that structure, engineers have already calculated exactly how much it can take, how long it should last, and what it would take to bring it down. The fact that you never think about any of that while crossing it isn't an accident. It's the entire point.